Hello. Hello. Good morning, everyone. Hello. Hello. Good morning, everyone. Hello.
Yes, Shohini. Good morning. Good morning, Ruchira.
Good morning, everyone.
So, good morning, Disha. Shubhodip, good morning. Shastik, good morning. Hongkong, good morning. So, canonical form of the linear module can you see me? I think not. Please wait. Please wait. Okay, I think there is a problem. Canonical form of the linear model, the usual Gauss-Markov model is given by This is the observational vector. Mean vector, and this is a dispersion matrix. We know we denote y curl as follow. A is a coefficient matrix or design matrix of order n cross p. And theta curl, theta 1, theta 2, theta p prime. Let rank of A equal to R, which is less than equal to P. Suppose alpha 1 curl, alpha 2 curl, alpha R curl be an orthonormal basis Please wait for 1 minute. Okay. Be an orthonormal basis of the column space of A now we can extend this orthonormal basis to an orthonormal basis of Rn by adjoining orthonormal vectors then we form a matrix P as follow. Then this P is a orthogonal matrix. That is P prime equal to I or P prime, P prime P also. Now define xi curl alpha I curl prime, sorry, this is xi, not xi curl, xi equal to alpha I curl prime y curl 1 to n, then you see that expectation xi equal to alpha I curl prime expectation of yi, y curl, and expectation of y curl is nothing but a theta curl, and this is xi I, and for I equal to 1 to r, where xi I not equal to 0, and this is 0 if I equal to r plus 1 1 to p. Why this happened? Because alpha r plus 1 to n also orthogonal to alpha 1 to alpha r, and since alpha 1 to alpha r is a basis of the column space of A, so alpha I curl also orthogonal to the columns of A where I from r plus 1 to p. Now covariance of xi comma xj is equal to sigma square alpha I curl prime dispersion of y curl alpha j curl. This is equal to this is equal to sigma square alpha I curl prime alpha j, and 0 if I not equal to j, and 1 sigma square if I equal to j. So this implies x1, this implies x1, x2, xn are uncorrelated, and dispersion of x curl, where x curl is a x1, x2, xn prime equal to sigma square in. So therefore from y1, y2, yn we pass on to x1, x2, xn such that expectation of xi is equal to xi I, where this xi I not equal to 0, I from 1 to r, and 0 if I equal to r plus 1 to p, and dispersion of xi I curve equal to sigma square in. Okay, so this means xi is give a full set of independent estimable parametric function. Okay. Moreover, any estimable parametric function will be linear combination of xi1, xi2, xi1, xi2, xi-r. Also, the blue of any estimable parametric function lambda curl prime theta curl is equal to sum over I from 1 to r ci xi I is given by I from 1 to r ci xi as xi is the clue of xi I, where xi I equal to lambda I curl prime a theta curl I from 1 to r. Okay. And the portion xr plus 1 to xn give n plus r independent linear functions, and since this functions expectation of this xi I from r plus 1 to n 0, so this belongs to error space. So any linear function sum over I from 1 to n ci yi will be a linear function of xr plus 1 to xn. Actually, any error functions, better to say error function. So any error function ciyi will be linear functions of xr plus 1 to xn. Okay. So have you any question? Please tell me. So this is the utility of canonical form. And it breaks into two parts. First part gives the base linear unbiased estimator, and second part gives the error function. Okay, so next portion is estimation under correlated model. Okay, Shubhodip. The usual model is y curve, a theta curve, sigma square I. Okay, obviously yi's are uncorrelated here, but if this not happen, that means yi's are not uncorrelated, so we assume yi are correlated, that is y1, y2, yn are n observations with expectation of y curve equal to a theta curve, and instead of dispersion of y curve, instead of sigma square in, now it is, since we assume uncorrelated model, sigma square b, where b is not equal to in, but b is known positive definite matrix. Okay, under these assumptions, we can also estimate parametric function since we know if b is a positive definite, so we can write b as a tt prime, where t is a non-singular matrix. Transform y curve to x curve such that x curve equal to t inverse y curve, then expectation of x curve is equal to t inverse expectation of, since non-singular matrix, t is a non-singular matrix, t inverse exists, so t inverse into expectation of y curve, that is equal to t inverse expectation of y means a theta curve, and we denote t inverse a by u matrix theta curve, where u equal to t inverse a. And dispersion of x curve, this is equal to t inverse dispersion of y curve t inverse prime, so this is equal to sigma square t inverse b T inverse prime, and B is a TT prime, and T inverse, we know T inverse prime equal to T prime T inverse, so this is equal to sigma square I. So using this transformation we see that x1 curve, x2 curve, xn curve, this new variable x1, x2, this is not curl, x1, x2, xn, I denote this by x curl. Okay, so these new variables are uncorrelated. Therefore, in terms of x curl, the model is expectation x curl equal to u theta curl and dispersion of x curl, which is equal to sigma square I. So this is the usual model, and we know under this model we know the base linear unbiased estimator, and so this lambda curl prime theta curl be an estimable parametric function if and only if this lambda curl prime belonging to column space of A, here it is U, row space of U, sorry, row space of U, okay, and row space of U, we know this result under uncorrelated model, and here U is nothing but a T inverse A, and row space of T inverse A is same as row space of A. So this implies lambda curl prime be an estimable parametric functions if and only if lambda curl prime belonging to row space of A. Hence, even if, so we can conclude that lambda curl prime theta curl is estimable with respect to the original model. Original model means uncorrelated model. That means dispersion of y curl is sigma square b. Actually, we know this result for correlated model, and under this transformation we see that this model reduced to a uncorrelated model, and under this uncorrelated model we know this result, and we see that this parametric function estimable if and only if lambda curl prime belonging to row space of U, which is same as row space of A. So this means lambda curl prime theta curl also estimable with respect to original model, that means this uncorrelated model. Okay, and converse also true, and converse also true. Let lambda curl prime theta curl be estimable, then blue best linear unbiased estimator of lambda curl prime theta curl is given by lambda curl prime theta curl hat, where theta curl hat is a solution which is Gauss-Markov theorem. Solution of what? Solution of U curl prime U curl. So this, because this result hold for uncorrelated model, so solution of this U curl prime U curl theta curl U curl prime U prime U theta curl equal to U prime X curl. Okay, and that is U means T inverse A whole prime T inverse A theta curl T inverse A prime T inverse Y curl. So this is equal to A prime T inverse prime T inverse A theta curl equal to A prime T inverse prime T inverse Y curl. So A prime actually this is same thing. Okay, and this imply so therefore the blue is lambda curl prime theta curl hat, where theta curl hat is a solution of the equation 1, which can be obtained by minimizing x curl minus u theta curl prime x curl minus u theta curl with respect to theta curl. So that is minimizing x curl minus x curl means T inverse Y curl minus T inverse A theta curl prime T inverse Y curl minus T inverse A theta curve with respect to theta. That is minimizing y curve minus A theta curve prime T inverse whole prime T inverse y curve minus A theta curve with respect to theta. That is y curve minus A theta curve B inverse y curve A theta curve with respect to theta. So therefore, from the above discussion, we conclude that one, lambda curve prime theta curve is estimable if and only if lambda curve prime belonging to the space of A. And second thing, rho of lambda curve prime theta curve is lambda curve prime theta curve hat, where theta curve hat is a solution of this y curve minus A theta curve prime B inverse y curve minus A theta curve. Okay, so please tell me, have you any question? Shubhodip, Shohini, Disha, Shastik, Ruchira, please tell me. Ankon. Can I wrap this portion? Oh yes, Shubhodip sir, original model means usual model. Original model means not usual model, Shubhodip. Original model is a correlated model, okay? And usual model is, oh Subhrojit, okay, thank you. And usual model is uncorrelated model, Gauss-Markov model, okay? Have you any question, Shubhodip? You have a Shubhodip, please tell me. Original model is a correlated model. Okay, Shastik. And usual model is a Gauss-Markov model, uncorrelated model. Okay, thank you. Thank you, Shubhodip. So please tell me if you have any question. Shubhodip asking a question, but please tell me if you have any question. Shohini, Shastik, Shostik, Subhrojit, please tell me if you have any trouble, any problem. No problem. And second approach, estimation. And second point is estimation, where, okay Ruchira, where the parameters of a some linear restriction. Okay. Consider model y curve A theta curve sigma square I. where theta 1, theta 2, theta p are subject to k consistent linear regression consistent linear restriction, that is h prime theta curve equal to xi, where h is a matrix of order k cross p, so xi is a vector of order k cross 1, and we denote the columns of h by h1 curl, h2 curl, h p curl. This is a matrix of known constant. Okay. And I already mentioned that this is a jth column of H, so it is H1j, H2j, H kj prime, j from 1 to p. Now expectation of yij, this is equal to and I denote this xi curl by xi1, xi2, xik prime, and expectation of yij equal to mu plus alpha I beta j. For example, and we know for this 2A ANOVA 1 observation parcel, we consider this two constant. Okay, so this xi curl should be a known vector, the vector of known constant, vector of known constant. And we proceed using two methods, method 1 or method 2. Method 1, by reducing the model with fewer parameters, with no restriction. And method 2, minimizing the error sum of square with respect to a parameter subject to the restriction using Lagrange's undetermined multipliers. So actually, suppose the problem is, suppose this is a model, and now theta 1, theta 2, theta p are subject to k constant or k linear restrictions, and assume that this k linear restriction consistent. That means this equation is solvable. This system of non-homogeneous equation is solvable. So this H is a known constant matrix, and this is a known constant vector. And for this, suppose we consider 2A ANOVAs, then we assume that summation lambda I equal to 0, alpha equal to 0, and summation beta I j equal to 0. So here H is suppose alpha curl is a alpha 1, alpha 2, alpha p prime, and beta curl equal to beta 1, beta 2, beta q prime. So this should be H is a 0, 1 p curl prime, 0 curl prime, 0, 0 curl prime, 1 p curl prime. So this is H prime. So sorry. So H is a H prime. This is H. So it should be HK. Please, this is my mistake. Please rectify this thing. HK, and this should be P and J from 1 to K. Please change this thing, okay? Because here we take H prime, okay? So H should be H1, H2, HK, because order of H is P cross K, and jth column of H matrix, which is Hj curl, which should be H1j, H2j, Hpj instead of Hkj. Please change this thing. So for this 2A ANOVA, our H prime should be this, and theta curl is 0, alpha curl prime, not 0, mu alpha curl prime, beta curl prime, okay, whole prime. So if we consider K consistent linear restriction, in that case we proceed either method 1 or method 2. In method 1, actually in method 1, by reducing the model with fewer parameters with no restrictions, and in method 2 we minimize the error sum of square with respect to parameters subject to the restriction using Lagrange's multipliers, okay? So this is the two approaches. So have you any problem regarding this up to this part? Just I introduce the problem, and So have you any problem regarding this? Please tell me. Before going to discuss method 1 and method 2, have you any problem? Ruchira, Shubhadeep, Shubhrojit, please tell me. Again I tell you this is the restrictions. Okay, Shubhrojit. Okay. So please rectify this H matrix and J curl, jth column of H, these two portions. It should be K. Okay, sir, can you repeat the formation of H? Formation of H. So see that. Suppose this is the restrictions. Okay, Shubhadeep. H11 theta 1, H12 theta 2, H P1, sorry, it is should be H11 theta 1, H21 theta 2, HP1 theta P equal to xi1, H12 theta 1, H22 theta 2, HP2 theta P xi2, K1 theta 1, HK2 theta 2, HK sorry P PK P this is H1K, this is H2K, and this is HPK theta P xi k. Okay, so this is the restriction, and I assume this is a consistent linear restriction. That means this equations, non-homogeneous equation is solvable. We denote this by H theta curve xi curve. Okay, for example, I consider this example 2A ANOVA with one observation parcel, and this is the H prime. You can check this thing. One curve prime means 1 1 1 prime. Okay, and this is a null vector. So if you multiply H prime theta curl, if you take theta curl is a mu alpha curl prime beta curl prime whole prime, then you get this thing, summation alpha equal to 0, summation beta j equal to 0. So under this restriction, our problem is to estimate theta curve and find best linear inverse estimate of linear parametric functions under these restrictions. Okay, so we proceed either method 1 and method 2, and method 1 tells you by reducing the model with a fewer parameters with no restrictions, and method 2 tells you in method 2 we minimize the error sum of square with respect to parameters subject to the restriction using Lagrange's multipliers. Okay, Shubhadeep. So Shubhadeep, actually H is a coefficient matrix. Okay, the formation of H for this case 2A ANOVA with one observation parcel, this is the formation of H. Another, if you consider one-way ANOVA, suppose one-way ANOVA expectation of Yij equal to mu plus alpha I plus mu plus alpha I and the restriction is summation alpha equal to 0 I from 1 to n. I assume that balance case. In that situation your theta is mu alpha 1 alpha 2 alpha p prime and h should be okay. So clear, Shubhadeep? Okay. Shubhadeep, please tell me, have you any problem? Shubhadeep, are you hear me? Please tell me, have you any problem? So method 1, the set of equation h prime theta curl xi curl is given to be consistent solution. The H matrix means what? Shubhadeep, H matrix, actually you asking, sir, should not it be in the second example? Shubhadeep, I do not understand what is your query. Okay, thank you. The set of equation h prime theta curl equal to xi curl is given to be consistent solution of theta curl. So actually consistent the set of equation at h curl prime theta curl equal to xi curl is consistent. So we know this implies general solution of theta curl is equal to theta curl naught plus b delta curl. Theta naught is a particular solution. This is a particular solution. And particular solution of what? H prime theta curl equal to xi curl. That means H prime theta curl not equal to xi curl, and B is such that or B is such a matrix so that H prime theta curl B is such a matrix so that H prime B equal to 0, that is column of B belonging to ortho complement space of row space of H. Row space of H prime, that is column space of H. Okay. Now we already denote H as H1 curl, H2 curl, HK curl, and number of independent columns of P equal to P minus S equal to S. Okay. Delta curl equal to delta 1, delta 2, delta S is arbitrary, okay. And delta is playing the role of parameters. Now the model reduced to expectation of y curl equal to a theta curl, and theta curl means this theta naught curl plus b delta curl, and this is equal to a theta naught curl plus a b delta curl. Then z, expectation of z, now I take z equal to y curl minus a theta naught curl. Then expectation of z curl equal to a b delta curl, and AB is, we take AB is delta curl. See that actually we say delta curl is playing the role of parameters because this reason. Now this transformation under this model, the parameter is delta curl. Okay, parameters are delta curl. So dispersion of z curl, this is equal to dispersion of y curl minus a theta naught curl is dispersion of y curl equal to sigma square I. So therefore the model think there is a technical problem. Please wait. Restart.
We will give you a new streaming. So